Before we get into the bulk of what this unit is about, which is rational functions, we're going to kind of back up a little bit and talk about a couple concepts that you should have learned in Algebra 1. That's direct variation and inverse variation. Now, the simplest way to think about direct variation and inverse variation is this. In direct variation, you have two variables. If one of the variables increases, the other variable is going to increase as well. And if the variable decreases, that's going to result in the other variable decreasing. An inverse relationship or an inverse variation does the opposite. As one value increases, the other value decreases. Well, there's a way for us to write those relationships in a mathematical sequence. So we're going to focus on that in this first lesson here. So we'll start with direct variation in this video. Now you can see just by definition, it's a relationship between two variables in which one has a constant multiple of the other. If you look at that from the formula sense, you'll see that y equals kx. It almost looks like a linear function with k acting as the slope. Well, in a lot of ways it is. The k is what we call the constant of variation. And of course you remember that the slope is a constant rate of change. So those two things are kind of similar. So you can think of the k and the m, so to speak, as being the same thing. Now, what we want to do is we want to learn how to write this k in terms of x and y. And so if we move the x over to the other side, we can see that k equals y over x. And this is very good for us because this is in a ratio form. And anytime you have a ratio, you can actually write that ratio as a proportion to compare it to another y over x value. And this will help us to find any missing values in a direct variation relationship type problem. So let's take a look how that would kind of play out. I'm going to do this. I'm going to work sample problem number 1 for you and set it up so you can see it. And then I want to see you try to work sample problem number 2 on your own based off what you see in sample problem number 1. So, alright, it says use a proportion to solve a direct variation. It says suppose y varies directly with x. Well, when y varies directly with x, we can basically say that y equals to kx, or as we saw earlier, that k equals to y over x. So if we already have a y value of 9 when x is equal to negative 15, we can say that we can create that 9 over negative 15. Now think of that as your scale factor, your constant of variation, your slope, whatever you want to do. But the last part of this question asks, what is y when x equals to 12? And this is where the proportion comes into play. So 21. So x equals to 21. We want to know what the y value is when x equals to 21. And there's your proportion. Now, you should remember from Algebra 1, maybe even all the way back to pre-algebra, that whenever you have a proportion, which is simply two ratios that are equal to each other, you use cross multiplication to solve for this. So we'll go ahead and do that. So that's negative 15y equals to 189, and y equals to negative 12.6. I went ahead and rounded it into a decimal. If you left it in fractional form, that's fine. Okay, so what I'd like you to do is sample problem number 2. You're going to be using a direct relationship, but this time it's in a word problem format, and you have to come up with the two variables on your own. Okay, so let's take a look at this. It says commissions vary directly with sales. So let's just go ahead and put our direct variation formula there. Now we have y and x, but this time we want to say something that represents commissions and sales. So we can actually change this to C for commissions. We'll still use our K, and we'll use S for X. So let's take a look. It says for $1,000 in sales, the commissions is $85. Well, what we can do here is we can either set it up in proportion format, or if you like, you can actually find the scale factor of value for K. So you can either do it like sample problem number 1, and if you did, that's perfectly fine. Or I'm going to show you another way to back into this in this method. So we can say that for $1,000 in sales, we have $85 in commissions. So $1,000 in sales. So basically our K here is going to equal to 85 over 1,000. Or if we want to break that down, that's 0.085. Now what we can do, it says the commission, what is the commission for 2,300 in sales? We can go back to this C, and now we have a value for K, 0.085, and then we want 2,300 in sales. So our commission for that would be $195.50. Now, what we've done here with our K, this ratio of $85 per $1,000 sales is our ratio. That K actually represents a commission rate, a constant rate or a constant of variation. And so we could say that basically this is 8.5% commission rate on every sale that they actually make in this particular problem. So that is a good start for direct variation. In the next video, we'll talk about inverse variation. Now for inverse variation, we have a different relationship between the given variables. We still have a K, which represents the constant of variation. The only difference is in the format of which we set up the equation, which gives K a very different implication. Basically what happens in inverse variation is that when one value increases, the other value decreases. And so this is different than direct variation. Now, to make that happen mathematically, we set up the equation as x times y equals k. So this time the constant of variation acts as a product of the two variables. And then we can write k as a ratio against either the y or the x, depending on how we need to use the k and or the variables that are given in the problem to solve that. So basically we need to first of all have the skill of identifying the type of problem we're dealing with. Are we dealing with direct variation or are we dealing with inverse variation? So that's what sample problem 3 is all about. So go ahead and try to answer sample problem number 3 and then write the function that it models. So give you a second to do that and then come back and check the solution. So if we look at this, the first telltale sign when we're given a list of input and output values, or if we were given a list of ordered pairs, or however you wanted to look at it, the very first thing that I would look for is as this values increase, notice that the y values are actually decreasing. And so whenever you have that, what you're basically looking at is an inverse relationship. Okay? Now, that being the case, if we wanted to model this particular problem, we would have to figure out what k is. And so the easiest way to do that is through any xy pairing, and we just multiply them together to get a value for k. And so if we took 2 times 15 to equal k, that would simply equal to 30. Notice no matter what pairing we take, if I did 4 times 7.5, I still get 30. If I did 10 times 3, I still get 30. So now I know that k equals to 30. It says write function models for the direct and inverse variations. And so basically we have an inverse variation, and so we can write y equals to 30 over x. And of course, if you wanted to write that in terms of x, that would work as well. But these are basically the two parts that you're looking to get. So now we have sample problem number 4, and it's a little different than what we had before. And you might want to use you're going to need your calculator here for a little graphing exercise. But we have an inverse variation, and we want you to write the model for the inverse variation, and then see what it looks like from a graphing standpoint. So go ahead and try that now. Okay, so if we look at this, it says suppose x and y vary inversely. Again, if that's the case, we know it's going to be x times y equals to k. And then we have 4 for x, 12 for y, so our k is going to equal to 48. And generally speaking, we write equations or models in terms of y equaling to something. So we'll stick with the y equals to k over x. Now, this is going to work nicely whenever we move into what we call the reciprocal function, because we already have it in terms of y equals. If you had this in terms of x equals to the constant variation over y, then if we want to graph that, we've got to start moving the parts around. So since we already wrote it in terms of a function here, we can simply plug this into your calculator. So if you went ahead and did that right now, you need to sketch what this graph looks like, and what you would basically see is this. We've got our axes, and then you would basically get a graph that looks something like this. It would have two parts, and it would look like what we call a reciprocal function, and that'll be the next lesson. So, and if you did a t-chart of this, you would see that as your x values increase, your y values would decrease, and so that would hold true for the inverse relationship. Now that we have reviewed direct variation and inverse variation, we can now start to combine different types of variation. And so you can see from the concept box that we have multiple types of combined variation. Now, the first vocabulary word that you need to become familiar with is joint variation, and this basically tells us when a quantity varies directly with two or more quantities. And you tend to see this a lot in geometry when we start to have multiple variables in a problem, such as in our volume problems. And so if you see joint variation, we're referring to a type of direct variation. And of course, if we say inverse, then we're looking to create something with a fractional form or denominator. So you definitely want to take the key concept summary box there and review that very carefully. Now, the easiest way to kind of learn these is trial by fire. So let's just jump in and do sample problem number 5, take a look at the solution, and then you can move on to sample problem number 6 and see how you do there. So go ahead and work on sample problem 5. Okay, so we start by giving us a cost of constructing a 9 by 12 foot patio, and it tells us that the cost varies jointly with the length and the width. And so we were given the length and the width, we were given a cost. So the cost varies directly or jointly with length and width. So we have our constant of variation there. And now I just basically take the information that's given and plug it in. If you're ever unsure of where to start, the simplest thing to do is just write your variation equation that you're going to use and see where everything fits. And you can see here that we have a k value. We don't know what our constant of variation is. So we'll just go ahead and work this out and solve for k. So k equals 6.8. Now, how are we going to use that? The question basically asks, what does an 18 by 14 foot patio cost? And so we're looking for cost here. And now that we have a k value, we can use that to help us find the total cost of an 18 by 14 foot patio. So in this case, we have $761.60, and so that gives us our final answer. So you can see here a multi-step problem where we're required to solve for k first so that we can use it to find the ultimate cost of a larger patio. Alright, very good. So hopefully, if you haven't yet, go ahead and try sample problem number 6 and then come back and take a look at that. Alright, so we have a little bit more going on here. We have a direct variation and we have a inverse variation, and so we need to apply some values or some variables to each of these parts. So it says the number of bags of grass seed N varies directly with the area. So we know that N varies directly with the area, so we have Ka. So if that were all we had was a direct variation, we'd be done. But it also is inversely related to the weight of a bag of seed. And so our inverse relationship, if you were to, so to speak, cover up the A value, you now have K over W. And so you have the direct variation mixed in with the inverse variation. And so again, we can take the information that was given to us and plug it in and then just solve for whatever the missing part is. And so if we look at this, it says it takes two 3-pound bags. All right, and then of seed to cover an area of 3,600 square feet. So we have 2 bags of grass seed. We don't know what our constant of variation is. We're looking for a 3,600 area of a 3-pound bag, the weight of a 3-pound bag. So there we go. And then we can simply solve for K. K is going to equal basically 1 over 600. If you plug that in and you got a decimal, that's perfectly acceptable, and you can go from there. Now, let me show you how we're going to use it. We want to know how many 3-pound bags, and this is kind of convenient because we're using the same weight here. How many 3-pound bags do we need to cover a 9,000 square foot area? Now, I'm going to go ahead and replace the K in our original equation. So that's going to be 1 over 600. And so if we look at that, that's K times the A over W that we had originally. If we look to combine this together, we're going to get A over 600W. Now, we can plug in from here. We want to know how many bags, so we're looking for N. The A is the area that we need to cover, 9,000 square feet. And again, we're still just using 3-pound bags. And so that gives us 5 bags needed for the 9,000 square feet of yard. Alright, so there's a combined variation type problem with both direct and inverse.